So a forward path gain is simply the product of the gains found by traversing a path from the input node to the output node of a signal flow graph in the direction of the signal flow. So let me illustrate it with an example. So let's say you have a signal flow graph, just a simple representation. This is a node, this is another node, a node, a node, and the direction, the system, and the blocks, and the direction of the signal flow. You have the input and the output, right? And let me do another branch here, and that. So the forward path gain, and then they have the gains G1, G2, G3, and G4. So the forward path gain. So first of all, you'd have to identify your forward path. And then the forward path is simply the path from the input node to the output node, right? And then in most signal flow graphs, we mostly have one or more paths from the input to the output, right? So if you look closely, you can see that we can move from the input node, which is here, to the output node here by moving from this side and then move straight to this side. That's our first path, right? And then our second path is from the input node. Then we trace this path, we pass here, and then that's our second path. Now the gain is simply you multiplying the gains on the systems. So if for the red path, right? So for the red forward path, the gains are G1, G2, and G3. So we can say that the forward path gain for the the red forward path is simply going to be, let me color code the whole thing to make this whole thing. Okay. So for the forward path, for the red forward path, the forward path gain is going to be simply the multiplication of the gains G1, G2, and G3, right? And then the forward path gain for the yellow or the for this color, I don't even know the name of the color. For the yellow path, right? Or for the yellow forward path is going to be G1, G4, and G3. And mind you, they should always be following the signal flow, right? So if I should have, let's say, a simplified signal flow graph with this going in this direction, that going in that direction, this going in that direction, and that going in that direction. And I have the inputs here, outputs here, and then this is going here, this going there, this going there, this going there. And then I have one which is right here and it's in the opposite direction. Okay, let me know when the thing is complicated. This side here, going here. And then they have gains of G1, G2, G3, G4, and G5, right? Let me change the direction here to make what I'm trying to. So the first forward path is from here to here, right? Because they all follow the same signal flow and it's from the input node to the output node. But then this path right here can't be a forward path because you have the input node coming in this way, and then since the direction of this branch here poses this direction, then it means that we can't go from the input to the output, right? So this path right here does not qualify. This does not qualify to be a forward path. Hence, there's no way you can find a forward path game. All right, nice. So the second one, the second term that I'd like to speak about is the loop game. The loop game. Now, to find a loop game, we have to first of all define what a loop is. So a loop is simply when you actually start from a particular node, you have to end on the same node without passing through the same node twice. All right, so it's much more easier when I show it. So let's say you have a simplified signal flow graph like this, right? It goes this way, it goes that way, it goes this way, it goes that way. This is your input, this is your output, and then this goes here this way, and this goes here this way. So let's say I start from a node, right? I start from this node. Then I traverse it from here. I'm following the signal flow to here. Then I end on the same node here. This becomes my loop. This is a loop. If I should take this node here too, and then follow the signal flow, I end up on the same node. And this also becomes a loop, right? Likewise, this is also a loop. If I should have this R of S, C of S, a huge one there. So if I should start from this node, right, and then pass to follow the signal flow, then I end up here at the same node. This also qualifies to be a loop, right? So the loop gain is simply trying to multiply the gains on the loop. So for instance, if this has a gain of G1, G2, G3, G4, G5, and G6, right? The loop gain for this particular loop here is going to be G2, G6, right? And then the loop gain for this particular loop here is going to be G3, G5, right? Likewise, too, if the gain on this branch is G1, G2, G3, G4, and G5 here, the loop gain for this particular loop is just going to be the product of G2, G3, and G4, right? Okay. Now, the third thing that I'd like to talk about is the non-touching loops, right? So for the non-touching loops, we have types. We have taking 2 at a time, taking 3 at a time, taking 4 at a time, depending on the complexity of your block diagram or depending on the complexity of your signal flow graphs. Okay. So non-touching loops. Let me draw at screen. So for non-touching loops, it's simply loops that do not have any nodes in common. Okay, so loops that don't have any nodes in common. Let me give you a simple illustration here. So let's come back to this side right here. Now you can see that these loops, right? These loops, they are touching each other because there's a common node here. This loop and this loop, they all have a common node here. Hence they are touching. But if you should have a loop in this fashion, right? This, that, another loop, R of S, C of S. So this is a loop, right? This is also a loop. So this loop and that loop qualify to be a non-touching loops because they do not have any nodes in common. right? Makes perfect sense that way. Now, let's move on to the fact that we can have non-touching loops taken two at a time and taken two at a time. Now, I can't actually illustrate this right here, but the more that we solve examples, the more you'd find that we have touching loops taken two at a time. So you just let me try and illustrate this for a while. So let's see, you have another one to here. This is this goes on this way, and that this goes on that way, and that. So we have this one right here. Silvers. So this qualifies to be a loop because I start from here and I end up on the same node, loop one. This also qualifies to be a loop. I start from here and I end up on the same node, loop two. This also qualifies to be a loop. I start from here, I end up on the same node, loop three, right? So in this case, L1, L2, and L3 are qualified to be non-touching loops because they have no node in common, right? So it's like we are trying to take individual loops that don't touch each other. So let's go to two non-touching loops, taking two at a time, right? So if I'm saying non-touching loops, taking two at a time, let me non-touching loops, taking two at a time, right? Then it's going to be L1 and L2 aren't touching. So they qualify to be non-touching loops, taking two at a time. Likewise to L3 and L1 and L3 are not touching. Those two also qualify to be non-touching loops, taking two at a time. I could also say that L2 and L3 are not touching because those actually they are not sharing any nodes in common. So if I want to write this, I can say that L1, L2 qualify to be a non-touching loops, taking two at a time. L1, L3 qualify to be a non-touching loop, taking two at a time. And L2, L3 also qualify. Mind you, I am not also trying to say L2, L1 are actually non-touching because I've said it here already. The L1 and L2 is the same as the L2 and L1. And I can't also say that L3, L1 are also non-touching loops, taking two at a time because I've already said it here, right? So it all must end here, right? So L1 isn't touching L2, L1 isn't touching L3, L2 isn't touching L3, L2 isn't touching L3. Now I could also graduate to non-touching loops, taking three at a time, right? So the taking three at a time is that I take three, then I see if they are touching each other or not, right? And it's clear from this example that L3, L1, L2, and L3 are not touching each other. So they all qualify to be touching loops, taking three at a time. So then I multiply the gains of the loops. So L1, L2, L3. Now, don't worry if this doesn't actually make sense. The more we solve examples, the more you'd actually see how these are, and then you'd get to appreciate them. Now, the next thing that I like to move on is the formula. Right? Let me skip. Okay. It's the formula. Since I said this is a more formulaic approach, then there has to be a formula somewhere that would make everything simple for you. So the first transfer function g of s is equal to c of s over r of s is equal to summation k always starts from 1 to n, right? Where n is the number of forward paths and t sub k delta K all over K. So I've already said this. Okay, K is the number, so N is the number of forward paths. And T sub K is the kth forward path. Is the kth forward path gain. Just like what we have here. You see, T sub 1 is the first forward path gain. T sub 2 is the second forward path gain. So that's the same thing that we have here. Now, the thing that I'd like to talk next is the delta here. The delta here is simply 1 minus the summation of the loop gains plus summation of non-touching loops. Non-touching loops. Non-touching loops. Taking two at a time. Taking two at a time. Minus summation of non-touching loops. Taking 3 at a time. Now take caution that you have the signs alternating. So there's plus here, and then there's minus, there's plus, and then there's minus. So the next one is definitely going to be a plus. Then it goes on that way, non-touching loops, taking 4 at a time, and it goes on that way. Now the delta sub K, I'll come to that one later, right? That one is much more. I don't want to confuse you by saying delta minus this one. When we start solving a question, you'd come to appreciate the function of the delta K here and what it represents. Okay, so based on everything that I've said, let's move on to solving the question. So before we simplified the block, we've done the signal flow graphs for this particular thing already, but I like what to skip it. The way I've arranged the question, I've arranged it in a way that it moves from easy to more difficult. So let's skip this one and let's come to this side. Okay, so this is the question now I'm trying to. Now, in the previous video, we've already drawn the signal flow graphs for this block diagram already. So I'm just coming to scribble it very quick and see. The lights went out, so everything is gone. Okay. So this is what we had. We said when I do it looks something like this. R of S. 1 G1. So the first step that you'd want to do when you're actually trying to reduce a signal flow graph is to first of all identify your forward path. Okay, and then we said the forward path is simply the path that links the input to the output, right? So from this diagram, I can see that there are numerous forward paths here. The first one is the one that moves from this side, then it traces this to that side. So that's my first forward path. And then my second one is from this side again. Then it branches off here. Then it goes to that side, right? Let's see if we can find a third one. Think that's all. So to find the forward path gain is simply going to be, let me write the forward path gain. So it's simply going to be, for the red path, it's just going to be the multiplication of the gains there. And it's going to be 1 by G1 by G2 by G3. I made a mistake. I think. Okay, G2. So it's going to be G1, G2, G3. That's for the red part. Now for the yellow part, which is 2, T sub 2, it's going to be 1 times 1 times G3, right? So it's just simply G3. So these are the forward parts that we have identified. We've seen that there's only 2 forward parts, and it's from here and then runs to that part. Let's go. Now, the third thing that you should do is to identify your, sorry, the second thing that you should do is to identify your loops, right? So we said that the loops actually start from a particular node, then it traverses the signal flow, and it ends up on the same node, okay? So the first loop that we can identify here is going to be this, right? It moves here, then it traverses, then it comes back. So let's call it L1. Let's see if we can find another loop. We can see that we can also start from here, right? And move here and also come in. No, that is not a loop. That can never be a loop. That should never be a loophole. Because I was thinking that now it's not a loop, and I'm sure you've seen it by now that it can never be a loop. Because if I should move from here to that place, this actually opposes the movement of this to that side. So this does not qualify to be a loop, right? So it means that we only have one loop and one rule, just one loop. Okay. So loop gain is simply the L1, which is minus G1 H1. It's minus G1 H1 because of the gains here, G1 and minus H1. Now, the next step is to find out if we have any non-touching loops. And then since there's only one loop, I doubt if we can have non-touching loops, taking two at a time, because we just have one loop, right? So the next thing to do is to approach it with the formula that we derived, which is C first over R of S is simply summation of k is equal to 1 to n T sub k delta k all over delta, where n is the number of parts that we have found so far, and in that case is 2. Okay, and then we know T sub k. That's what we have here, the T sub 1 and T sub 2, right? So the only thing to find right now is the delta, and the delta we know from formula that is 1 minus the summation of the loop gains minus the plus the summation of non-touching loops, but we are not going to add that term for now, right? Because I'm starting from the easy questions and I'll graduate to the difficult questions with two non-touching loops, taking two at a time and all of that, right? So we can simply put in our formula. So summation of the loop gains is simply, since you have only one, is going to be minus G1 H1. and it's 1 plus G1 H1. This is what we get. And the next thing to find is our delta sub k. So our delta sub k, we can see that delta sub 1. Now, the reason why I didn't want to add a formula for this in the introductory part is because the delta sub k is simply what is left after you eliminate all the loops touching that part. So, for instance, for the delta sub k, for the delta sub 1, we actually identify the first part, right? Which is from here to this side, right? And then we identify the loops that share a common node with that part. If a loop shares a common node with that part, then we take it out, right? So that's what the whole thing is about. So we just take it out from this side, right? So if we take this loop, right? This loop, so this part from here to this side, the first part. And then since there's only one loop, we can see that that loop has two common nodes with it. So we take it out. So we take that loop out from this side, right? So we cancel this out. And then we are left with what? 1. And then our delta sub 2 is the same thing. We identify the second part, right? And then we see if this loop has a common node with that part. And of course, there's a common node here. So we eliminate that loop from this side, right? So we take that loop out, the gains of that loop out, and then we get 1, right? Now, if you don't understand, you can rewind and then watch the whole thing again. Or if I move on to the next question, it will become clear to you, right? So then we can use the formula. You can see that T sub 1 delta 1 plus T sub 2 delta 2 all over delta. And now T is what we found here. G1, G2, G3 multiplied by 1 plus T2 is G3, just G3 multiplied by delta sub 2, which is just 1. And our whole delta is 1 plus G1 H1. And I can simplify this to be G3, G1, G2 plus 1 all over 1 plus G1 H1. Right, so this is the transfer function. And mind you, we did not have to move any block, just like the way we did in the previous videos where we had to move this summing junction and pick off points. This is a more formulaic way of doing stuff. So we don't have to go through the pain of taking a summing junction ahead of the block or taking a pick off points behind of a block or blah blah blah. This is a more formulaic way of doing stuff. Okay. Now the second question that I like to solve is this. Let's move on to a less complex one. This seems less complex. Okay. So when we converted this diagram into its signal flow equivalent, we had this. You can forward it fast to not waste your time. Let me just draw it very quickly. U of S 1 over S minus 1. There's 1 over. The signal flow should always be in the middle. Okay. and then you have a large one from that side. So the first step is to identify your forward path, right? So the forward path, I'm going to say it again, is simply the path that links the input to the output. And if you can't find any forward path at all, then at least what you should find is just the straight line from the input to the output. That should be your first forward path. So forward path gain. The first one I've identified, the first forward path is T1. And then it has, no, I forgot to write the gain here, 1. And then it has the gain 1 times S squared times 1 over S. So it's 1 times S squared times 1 over S. So when you simplify, you get S. Now, the second forward path that we can identify is this side. Then we branch off this side. And then we come back here. Right? So that's the second one that we can identify. We start from here. Then move here. Then move there. So T sub 2 is going to be the 1 times the 1 over S times the 1 over S. Right? So 1 times 1 over S times 1 over S. Let me see if I've missed anything. No, it's still the same thing. It's still the same thing. Okay. And then if you simplify that down, it gives you 1 over S squared. Now let's see if you can find the third path. This path here does not qualify to be a forward path. This one also does not qualify to be a forward path. So we have just 2 forward paths. Now the next thing to do is to find your loops, right? So the loops is simply you start from a node and then you follow the signal flow, and if it ends on the same node, and then you have a loop. That's the easiest explanation I could give it. So loop gains. So let's start. The first loop that I can identify, right, is the loop that you take when you start on this node. And then you traverse, you follow the signal flow, and then end up on the same node. That's my first loop, right? So I can see that L1, the loop gain associated with this loop is just going to be minus 1 times 1 over S. And it gives me minus 1 over S. Now, the second one too that I can identify is simply I start from here, right? The same node here. Then I traverse this path. I end up on the same node. And I'm following the signal flow. So my second loop is therefore minus 1 times S squared. Minus 1 because of the gain here, and S squared because of the gain here. And it gives me minus S squared. Now, what's the third loop? The third loop is very difficult to find unless you practice and then you shine your eyes very, very well. All right. And I'm sure most of you have seen it and are shouting at the screen. I've turned into the Dora the Explorer. Have you seen the loop? They are saying yes, yes. So the third loop is going to be I start from this node, then I move here, and I come back here. That's my third loop, right? So my loop gain is going to be L3 S squared multiplied by 1 over S multiplied by minus 1. So S squared 1 over S times minus 1. And S cancels 1 over S here. And I get minus s. Okay, that's it. That's it. Now the second thing to do is to identify your non-touching loops or your non-touching loops taken two at a time. And then since you can see that all the loops share a common loop, we can, since you can see that all the loops here share a common node, we can boldly say that there's nothing like touching loops taking two and three at a time. Because you can see that the green loop here share a common node with the yellow loop here. And then the red loop here shares a common node with the green loop here and then the yellow loop there. So there's no non-touching loops taking two at a time or three at a time, right? So the next thing that we move on to is the formula. S over R of S and then E A. Summation starting from K is equal to 1 to the number of parts that we've identified so far. And in this case is 2. T sub K, this all over that. Now we know what our T sub K is, right? That's T sub 1 and T sub 2. The only thing left to find here is the delta. And then from the delta, we can find our delta sub K. And then we know that the delta is 1 minus summation of loop gains, right? Plus summation of non-touching loops. But since you have none here, I like to omit it for now, right? So 1 minus summation of the loop gains. I have 1 minus 1 over S minus S squared minus S, right? And I can simplify it to 1 plus S squared plus S, right? Okay, now the next thing to find is our delta sub K. So the delta sub K, let's find the first one. So since the first one, then we have to look at the first forward path that we found, which is from this side, the straight line from the input to the output. And then look at the loops that have common nodes with that forward path. And if we do find one, we take them out, right? So this is the first forward path, right? And I can see that the green loop has a common node with that first forward path. So we eliminate the green loop from this function here. So for now, concentrate on what I've done here. Concentrate on this for me, right? For guess what I've written here, just concentrate on this, right? So if we should take the green loop gain from this one, we can see that the green loop gain is 1 over S, right? So you can just take this one to 0, right? So you can also see that the yellow loop has a common node or shares a common node with the first forward path. So we take that one to out. So we take the gain out. So the gain of the yellow loop is minus S squared, right? And then we likewise to look at the red loop, right? It shares common nodes with the first forward path. So we take that one to out. So what you are left with is 1. That's for the delta 1. Now for the delta 2, we do the same thing. We identify the second path, which is from this side, then it passes through here, then it goes here. That's our second path. And then we identify the loops that share a common node with the second path. Now, if you do your eliminations, you find out that we'll get 1 here too, because every loop here touches the second path, right? So this one too gives us 1. Now, the next thing to do is you come back to the formula, then you substitute whatever that you have here. Then the whole thing becomes simple. Let me clean this side. Squared. Okay. So I can see that T sub delta 1 plus T2 delta 2 all over delta. So T1 is what we found here to be S multiplied by 1 plus T2 is minus, so T2 is 1 over S squared multiplied by 1 all over the delta, which is what we found here. So it's 1 plus 1 over S plus S squared plus S. This gives us S plus 1 over S squared, 1 plus 1 over S plus S squared plus S. Now I could simplify this by just multiplying the denominator and then the numerator by S squared. When I do that, I'll get S cubed plus 1 S squared plus S plus S raised to the power 4 plus S cubed. Makes sense, right? Does it make sense? So I made a mistake trying to find, so as you can see, the transfer function of this branch right here is minus S. But then I wrote minus 1. Minus 1. So it's supposed to be minus S. So in that case, let me start the whole thing again. Okay, so the next step is to find the loop gains. So the loop gains are simply, you find a node and then you trace the signal flow. And if you end up on the same node, that's a loop. Now, the first loop that I like to identify, the easiest one of all, is I start from here. Then I move this side. I end up on the same node. Right? So my loop gain is going to be L1. I multiply the gains involved, S squared multiplied by minus 1, and it gives me minus S squared. Now, the second loop is I start from the same node here. I follow the signal flow, and I come back here, right? So my second loop gain is going to be S squared multiplied by 1 over S multiplied by minus S, and I get minus S squared. Now my third loop is a little bit tricky. You just have to shine your eyes to see. I start from the same node here. I move here. Consider I'm tracing the signal flow, and I end up on the same node. So my L3, so it is supposed to be L2. My L3 is going to be 1 over S multiplied by minus 1 is equal to minus 1 over S. Now, from what you've seen so far, there's not going to be any non-touching loops taking 2 at a time or taking 3 at a time. You can actually see that every loop shares a node. So there's no way that the 3 loops here, are touching each other. So there cannot be any non-touching loops taking 2 at a time or taking 3 at a time. Right. So let's just move on to the formula. We have C of S, R of S gives us summation as we start K from 1 to the number of the fourth part, which we've seen to be 2, T sub K all over delta. So we know what T sub K is, and then we can find this one. And from this, we will find delta sub K. So delta is going to be 1 minus summation of loop gains. I'm not going to add the term that involves the non-touching loops taken two at a time because we do not have that here. So 1 minus s squared minus 1 over s. I summed the loop gains minus s squared minus 1 over s. Right? I can simplify it 1 plus s squared plus s squared plus 1 over s. And this gives me 2s squared. Right? And the next thing to do is to find the delta sub k. So the delta sub k, let's start from 1. So the delta sub 1 means that you have to look at your first forward path. And in our case, our first forward path is from here to this side and that side. And then the next thing to do is to identify the loops that have a common node with that first path, right? And as you can see, the red loop has common nodes with the first path. The green loop has common nodes with the first forward path. And then the yellow loop also has common nodes with the first forward path. So hence we take all of them out. We take all of them out from this delta right here. So right now I need you to focus on this term right here. Right. So since we said that the red loop touches the first forward path, we take that one out. Right. The yellow loop too touches the first forward path, we take it out. And then the green loop too touches the first forward path, we take it out. Right. So what you are left with is just 1. It's 1 minus 0. And that's all we are left with. So it's just 1. Now the delta sub 2 too, you look at the second path and in our case is from here, then it traces the side, then it goes to the output, right? So you take note of all the loops touching the second path and then you take them out of what we have here, right? So from looks of things, you can see that the green loop has a common node with the second forward path, right? So we take it out. So we take that one too out. And then you can see that the red loop has a common node with the second path. So we take that one too out. And then the yellow loop too has common nodes with the second forward path. So we take that one too out. So what are left with is just 1 minus 0, which is the same as 1. Right. So the next thing to do is just to use the formula to find our overall transfer function. And it's going to be, we expand this T1 plus T2 all over delta. And then T1 is what we found here already to be S. So S multiplied by delta sub 1, which is 1, plus T2 is 1 over S squared multiplied by delta 2, which is 1, all over the delta here. 1 plus 2s squared plus 1 over s. Can simplify this to give us s plus 1 over s squared all over 1 plus 2s squared plus 1 over s. To make things easy for me, I can multiply both the denominator and then the numerator by s squared. Then I'll get s cubed plus 1 all over s squared plus 2s is the power 4 plus s. So this is my final transfer function. I did not have to move any blocks or move any summing junction or pick off points ahead or behind of a block. It's simple that way. you use the formula and all of that. All you have to do is just to identify your forward path gain, your loops gain, your non-touching loops, taking two at a time, and then use this formula to, find your forward path transfer function, to find your transfer function. Okay, let's move on to the next question. It's recording. Is it? Yeah, it's recording. The next complex one. Okay. So this one, let me see if yes, I have it here. So the signal flow graph equivalent is going to be, you can fast forward it because I'm about to draw it from scratch again. Starts here. Squared 50 over s plus 1 s. Mhm. Minus 1. And what of s? Your s. I'm putting everything into it. Okay, wait. So the first thing to do is to identify your forward path, right? So, like I said, if you don't know how to identify your forward path, or if it's difficult for you to identify your forward path, the first forward path that you should see is the straight line that you draw from the input to the output, right? Provided it's following the signal flow. Okay. So forward path. So the first forward path, T sub 1, multiply the gains involved. Is 1 times 1 over s squared times 50 over s plus 1 times s. Then this gives me 50 over s plus 1. Now the second forward path is going to be from this, help me out here, this and that, and that's it. So the forward path gain is 1 times 1 over s squared times minus 2 over s. So times 50 over s plus 1 times minus 2 is equal to minus 100 s squared s plus 1. The next step is to identify our loops, right? So we've been able to find the forward path transfer function. The next thing is to find our loops and hence the loop gains. So the loop gain from principles is you start from a node, then you follow the signal flow. If you end up on the same node, you have a loop. So let's start from this node right here. I follow the signal flow, and now my first. So my first loop, the green loop, is going to be minus 2 over s times 50 over s plus 1. And that gives me minus 100 over s multiplied s plus 1. And then let's see if we have any other node that we can identify. So let's see if I should start from this node here, right, and follow the signal flow to the output, then branch back to it. I have a loop. So my L2 is going to be 1 over s squared times 50 over s plus 1. Let me write my SO. S plus 1 multiplied by s multiplied by minus 1. It gives me one of the s's cancels the s's here. I get 50 minus, right, minus 50 s plus 1. Okay, let's see if we can find another one too. The third one, you'd have to shine your eyes. If we don't, it will trick you, right? So the third one is I start from here. I move this side. Then I follow this one. I end up here. So my third loop is going to be L3, which is 1 over s squared. So my loop gain for L3 is 1 over s squared times 50 over s plus 1 multiplied by minus 2 multiplied by minus 1. Right. I want to show. Okay. So the loop gain is going to be minus is positive. I get 100 over s squared s plus 1. Now, if you feel like I've made a mistake or I've missed the loop or there's another part somewhere, you can just come by the TU's office. If you don't find me there, I'm mostly at the library 3rd floor. Yeah, or you can text me or give me a call to find my way about, and I'll come to where you are on campus. Not to your hostel, to where you are on campus. Okay, so yeah, let's see if we can have known touching loops sticking to at a time. And it's impossible because every loop here share nodes, right? You can see that the red loop shares a node with the yellow loop and it shares a node with the green loop. So it's very difficult for you to have touching loops sticking to at a time and taking two at a time. So for now, we skip it. And the way I've arranged the questions is that I'm solving the easy ones, first, just to make you abreast with finding the forward path gain and then the loop gains and all of that. The questions that will come next, they will have the two non-touching loops. So the non-touching loops taking two at a time to actually, make you feel how difficult the whole thing is. But for now, you are still on the nursing field trying to solve the easy ones with you, then we'll graduate to the more difficult ones. So the next step from here is to use the formula. So you have C of S over R of S is equal to summation starting from K is equal to 1, and then you end up to from K is equal to 1 to the number of parts you have here, which is 2. T sub K all over this. Now we already know what T sub K is from what we found here. The next thing to do is to find our delta, which is 1 minus summation of loop gains. So 1 minus hundred over s plus 1 minus 50 over s plus 1 plus 100 over s squared s plus 1. Can decide to simplify it. You get 150 over s plus 1 and minus 100 s squared s plus 1. Right. Now the next thing to do is to find your delta sub k. All right. So let's start from 1. Delta sub 1. What this means is that we have to identify the first forward path. And in our case, the first forward path is from here to here, right? And take note of the loops that have a common node with the first forward path and take them out from this expression here, right? So if you look, or if you inspect the signal flow graphs, you can see that the green loop shares a common node with the first forward path. Hence, we take that one out. So the green loop has a loop gain of this one. So we take it out, right? So this goes away to 0. And then if we inspect again, you can see that the yellow loop also shares 4 nodes with the first forward path. So we take that one too out. So this one too goes away, right? And if you look closely to the red loop shares nodes with the first forward path. So we take that one too out. So what are we left with? We are left with just 1. 1 minus 0 and the same thing as 1. Right? And then the delta sub 2 too. We take note of the second forward path, which is from here. Then it goes to there. Right? And then any loop that has or that shares a common node with that forward path, with the second forward path, we actually take it out. Now, from what you've listened to so far, everything touches the second forward path. So every loop goes away. So we have 1, right? Then afterwards, we can boldly use a formula. Can say T sub 1 delta 1 plus T sub 2 delta 2 all over delta. Let me, I don't want to. So I'm continuing here. So this T sub 1 is 50 over S plus 1 multiplied by delta 1, which is 1, plus T sub 2 is minus 100 over S squared S plus 1 multiplied by delta 2 all over delta, which is 1 plus 150 S plus 1 minus 100 S squared S plus 1. Now I can simplify this by multiplying both the denominator and then the numerator by S squared multiplied by S plus 1. Now when I do that, I'm doing this straight from my mind, 50S minus 100 all over S squared S plus 1 plus 150 S minus 100. So this gives you S cubed plus S squared plus 150 S minus 100. Right. And I can compare it with the answers that we got from simplifying block diagrams. The one that we use the movements of the pickoff points and then the summing junction to see if we get the same thing here. If we don't, then you have to go like over it and do it and see if you get the same thing. Or you can come by the TA's office and see us. Okay. The next thing to do, let's see if we have another complex. Okay, we've already done this. Should do this. Yes. Okay. So the next thing to let me see if I have it drawn here already. Yes, drawn. Then you have to draw from scratch again. This light out to Okay, so let's see if we can draw it from scratch again. Okay, so the first thing that we should do is identify our forward paths. And then based on what we've seen so far, the first forward path that should be easy to be identified is the one that runs straight from the input to the output. Like the straight line exactly here, provided you have the same signal flow. Yes. So forward. So for the first forward path, T sub 1, the gain of that path is just G1 and G2. And then the second forward path, we can see to be I pass through the side, then I follow this curve to the output, right? So that's my second forward path is going to be just G3. Let's see if we can identify any forward paths. If I move from here to here, it's not really possible because this one is in the opposite direction. If I should move from here, then I continue this way. I can't branch here because this one is in the opposite direction. So we can only have two forward paths, and hence these are the gains that we've gotten. The second thing to do is to identify our loops to find our loop gain. So the first loop from principles, you know that once you start from a particular node and then you traverse the signal flow, you should end up on the same node. And when you do that, you have a loop. So the first loop that I can identify is just the main one here. I start from here. Then I follow the signal flow to the output. Then I follow the signal flow. Then I come back to the same node. Hence, my first loop, L1, is the gain associated with my first loop is going to be G1, G2, and H. Right. Let's see if we can find the second one. The second loop that I could find to is if I should start from here and then traverse this path and that path. I'll get the second loop gain to be minus G2, minus G2, G4. Okay, let's see if I could find the third loop. Can I find the third loop? Don't skip me. This, already done this, already done that. I can find this loop. Okay. So my third loop, I start from here, traverse this path. Now here, so my third loop, the gain associated with it is minus G3 and H. Let's see if I can find the fourth one. Is there a fourth one? Yeah, let's see. I've done this right here. Follow this. I come back here. I don't end up with the same node. So it doesn't qualify to be a loop. Move here. I think that's it. So far, we found only, and that's it. Yeah, that should be it. If you find any loops, you know where I am. You can just come to me, and then we can talk things out. Okay. So the next thing to find is to see if the loops are touching each other. And from the looks of things, every loop here share a node. So this node here, um, the the red loop has a node here, the green loop has a node here, and then the yellow loop too has a node here. So there's no way that we can have touching loops taking two at a time, taking two at a time. Don't worry, we'll by all means take an example that involves us to involve that would need us to find the non-touching loops. taking 2 and 3 at a time. But for now, I'm still trying to take things slow and easy. Okay. So we put our formula from here. So C of S, R of S is equal to summation starting from K is equal to 1 to the number of forward path. And in our case, is 2. T sub K, and that's all over delta. So the first thing to do is to find our delta, since you already know what T sub K is. And from our delta, we can find our delta sub K. So our delta is 1 minus summation of loop gains. Okay. 1 minus the summation of loop gains is minus G1, G2, and H. Minus G1 and G2 and G4 and minus G3 and H. So you can simplify this 1 plus G1, G2, H plus G2, G4 plus G3 and H. The next thing to do is to find our delta. So the delta sub 1 is simply we take note of our first forward path, and then we find any loop that has a common node with our first forward path. And if we do find one, we take them out of this expression here. Okay, so our first forward path is from here to here. And as you can see, every loop is touching that one. Every loop has a common node with our first forward path. So everything here goes to 0, and what we are left with is 1. Okay, I hope it's clear. And then delta 2, you can see that we first of all find our second forward path, which runs from this side to that side to that side, and identify the loops that have common nodes with that one. And then you can see that the red loop has a common node with the second path, right? And that common node is here. So the red loop is not part of it. And you can also see that the green loop has common nodes here and here with the second forward path. So we eliminate that one from this delta here. And you can also see that the yellow loop too has common nodes here and here with the second forward path. So we take it out, right? So what you are left with is 1. And I know by now that these you are actually getting used to how to find the delta 1 and delta 2 and then the delta, right? So after you found all these, the rest becomes easy. You just have to put the formula T1 delta 1 plus T2 delta 2 all over delta. I'm continuing here. So you can see that our T1 is what we found here. G1, G2 multiplied by 1 plus T2 is just G3 multiplied by delta 2, which is just 1, all over delta, which is what we found here. So 1 plus G1, G2, H plus G2, G4 plus G3, H. Now it has come to my attention that while we're solving for the block diagrams, reducing the block diagrams to a single transfer function, I did not include the H. I made H here 1, right? Yeah. And then thanks to Lily Manti for pointing that out. Yes. So you can actually see that if you watch that video, I did not bring H here because I thought, like, I assumed the H to be 1 because when I was drawing the whole thing, I made that part 1. So you actually get the same thing. And G3. A simplified version gives you G1, G2, H plus G2, G4, G3, H. Okay. Let's move to the next question. I draw this whole thing again. C5. Let's solve this question. How to instead, okay, before we solve this, okay, let's solve this. Can you give me a minute to draw the signal flow graph for this?